Hello, everyone, for this first SIPTA seminar of the academic year. So it was supposed to be in September, but we are almost in September, approximately in September, I would say, still. And today, I'm very happy to have as our first speaker, Uncertainty. So I will say no more, but he's a very active member of the community and also in machine learning. We could consider him as a rising star, also very active in animating the community. I will not give more details because the chair of these seminars will be done by Krik or Krik Amolumuande, who kindly accepted to share the seminar. So we will give you more details about Michele, already impressive but very young career. And so I hand the floor to you, Krik, and then Michele, you can start.
Yes, thank you so much, Sebastian. So as Sebastian already mentioned, I think we are very fortunate today to actually have the opportunity to actually listen to Michele talk. And as Sebastian mentioned, Michele is a rising star. He's also, in my opinion, he's a rising star. I think he has done quite impressive work. I mean, that catch a lot of attention of people from machine learning community, including myself. So I get to know Michele, I think last year. And then I was reading one of his paper at NeurIP, and at that time, I basically just started looking into imprecise probability, and then his work gave a lot of inspiration as well. And then we started working together ever since. So Michele is currently a lecturer in machine learning in the Department of Computer Science of the University of Manchester, and also a member of the Manchester Center for AI Fundamentals. And before joining the University of Manchester, he was a postdoc at the Department of Computer and Information Science of the University of Pennsylvania, and he did his PhD in statistics at Duke Universities. I would say that he's done quite a lot of fundamental work. You could say he's pioneering the area that I would call imprecise probabilistic machine learnings, right? And has received a lot of awards, including IJA Young Researcher Award. So in my interaction with him, right, we have been writing paper together. In my interaction with him, I'm sure that you will enjoy his talk today. So I hand over the stage to you, Michele.
Thank you very much. I hope I live up to the expectations that you set me up to, Krik. So thank you very much to Sebastian, to Krik, to everyone for inviting me here and for attending here today my talk. The talk is titled Conformal Prediction and its Uncertainty Quantification Capability via credal sets, which is a mouthful, but I hope you'll enjoy it. So for those of you who are very quick, this is a snapshot of the paper. If you cannot QR code it right now, it's titled The Joys of Categorical Conformal Prediction. So even if you just look for joys and conformal, you'll find it. Apparently, there are fewer people than myself enjoying conformal prediction. Now, before I start, I wanted to tell you about the motivations that led me to this kind of research. That is, conformal prediction is a very popular method in machine learning for statistical prediction, in fact, and it allows to quantify uncertainty in an ordinal way. What this means, it will become more clearer in a few slides. My research question is whether it can do so cardinally. That is, if not only the ordinal representation of uncertainty is possible, but also the cardinal one, and I'll be more precise about it in a few slides. And what I've found is that this journey of answering this question lead to other interesting discoveries. So I know many of you must be familiar with conformal prediction, but what I'll do right now is to go over it once again so that everybody's on the same page and you know what notation I'm using. Also, by the way, this talk is more on the theory side of things, so I apologize in advance if there are not enough pictures, or yeah, I should improve on that. Anyway, so for conformal prediction, we consider an exchangeable process, y1, y2, and so on, with a distribution P. And each yi is a random element taking values in a measurable space y sigma y. Remember that the sequence is exchangeable if for every natural number k, the joint distribution of y1 through yk is the same as the distribution of y perm 1 through y perm k, where perm is any possible permutation of those k many elements. What we do in conformal prediction is observe the first n element of the process, and with this data, plus the assumption of exchangeability, our goal is to predict the next observation using a method that is valid or reliable in some sense. Now here you have a very simple schematic representation where we have our training data in the bin on the left, and given our choice of confidence level alpha and a non-conformity measure psi, which I will go over in the next slide, but basically measures how much the next candidate elements is conformal to or similar to what we've seen before. The procedure gives us a prediction region, which is the pink oval on the left, that has some nice probabilistic properties. Okay, so to be a little bit more precise, let me denote by y capital N plus 1 the data that we have observed up until time n, and the next observation yn plus 1. After that, we consider a transformation through a vector t, which I denote by t superscript n plus 1, whose entries are t1 through tn plus 1. And every entry is defined by the following rule, that is, the ith entry for t is a function psi that is evaluated at the element yi of what I've seen so far, and everything else except yi itself. Okay. As you can imagine, this is a fixed function, and it must be invariant to permutation in its first argument. A very simple example could be the absolute value of the difference between the mean of everything else minus yi, so the ith element. This function is called a non-conformity measure, and its value is going to be small if and only if yi, so the ith element, agrees with or is close to a prediction based on all the other elements that I collected so far. Okay, now, for those of you who are following more actively, you may have noticed that I'm asking you some suspension of disbelief, right? Because I'm asking you to include in yn plus 1 this element y lower y subscript n plus 1, which is exactly the prediction target. We haven't observed it yet. But the exchangeability preserving properties of the transformations ti give us a procedure to rank candidate values for that yn plus 1. And to be more precise about it, let me present to you the full conformal prediction algorithm, which is the type of conformal prediction that I'm going to consider in this talk and in the paper. So we have the data that we collected, yn. We select a non-conformity measure psi, and we have a grid of candidate values for n plus 1, right? So if the space y is finite, this will be all its values. Otherwise, we consider a plausible grid. So for example, if we have the unit interval, this is going to could be 0, 0, 5, 0, 1, 0, 15, 0, 2, and so on. For each value in the grid, what we do is the following. We pretend that the next observation, that the next realization, is exactly the y tilde in the grid. We write the vector as the data that we collected plus the fictional, let me call it that way, next observation. We compute the transformation for all possible elements of this augmented data vector. And then what we do is we evaluate what is called the conformal transducer. As you can see, the conformal transducer counts how many times the transformation for all the observations exceeds the transformation for the n plus 1. And this sum, right, this count is standardized by the number of observations. And after all these computations, we return the value of the function pi for every candidate value on the grid. So In this way, we define the data-dependent function pi that returns to every candidate value its evaluation by the conformal transducer, which is in 0, 1. And it can be interpreted as a measure of plausibility of the assertion that the next observation will actually be that y tilde, that grid value, given the data that we've seen before. And okay, as I told you before, this is called conformal transducer by Vovk and his co-authors, who are the people who invented or introduced conformal prediction. Sorry. Now, the values of the conformal transducer are then used to derive what is called a conformal prediction region. This conformal prediction region is built as follows: give me all the elements in Y, or in, if this is impossible, the elements in the grid, such that their evaluation according to the conformal transducer clears the bar alpha that the user selects. It satisfies a very nice marginal probabilistic guarantee, which is the one you see on the slide. That is, the probability that the true realization for the next observation being in the prediction region that we derived before is at least 1 minus alpha, uniformly in N and uniformly in P. That is, and no matter how many data points we have in the first place, and no matter which exchangeable distribution we consider. Now, of course, this is a less ideal than what we want, right? Because here in theory, we would want something, a conditional guarantee, right? Given that yn is actually equal to yn, so given what we have collected, but this could be interpreted as an unexpected probabilistic guarantee over all possible realization of the data that we've seen before. Okay, so this slide is simply telling you that the whole conformal prediction procedure can be written as a set-valued function or correspondence. Remember that a set-valued function or correspondence is a function that takes inputs and spits out subsets of the range space. Okay, and in this case, we have a correspondence that I call kappa, which takes as input the confidence level alpha, the data that we have collected, and the choice of your nonconformity score. So this script F is the space where the nonconformity scores live, and it spits out a prediction region, which is exactly the conformal prediction region. Now, here I've only opened it up so that it's clear the dependency on the choice of the nonconformity score and on alpha. But this is exactly equivalent to this formulation right here. Okay, so by the way, my fixation with correspondences will become clear in a few slides. This is just to keep in your mind that conformal prediction can be expressed as a correspondence. Now, let me explain you my research question. So where does it come from? So conformal prediction region depend only on the ranks of the nonconformity scores. That is, if I consider a strictly increasing transform F, the conformal prediction region associated to a nonconformity score is exactly equal to the conformal prediction region associated with F composite to that nonconformity score. And related to this, if we can express the diameter of the conformal prediction region, which is the case when the space Y is at least metrizable, then there is no canonical cardinal scale for the amount of uncertainty. This means the following: that if you give me two conformal prediction regions, one whose diameter is 3 times the other, the only thing that I can say is that the one having the larger diameter encodes a larger uncertainty, but not that it encodes 3 times as much uncertainty as the other one. And so in turn, we can say that natively, if we only look at this classical way of conceiving conformal prediction, CP only supports ordinal comparison and not cardinal arithmetic. And this kind of drove me up the wall. I couldn't believe this. It's like this is too elegant, too powerful, and also too widespread to not have this cardinal ability to quantify uncertainty. So a few steps in the right directions were made starting from Leonardo Cella and Ryan Martin in the early 2020s. And then myself and other co-authors like Yusuf and Eike did something in the right direction later. So to go in the right direction, what I have to tell you is that, okay, this is just notation. I will call delta y the space of probabilities on y, and a credal set I will denote by calligraphic M. So what Leonardo and Ryan did in 2022 is to show that under an assumption that it's called consonance, that is that the conformal transducer actually attains its maximum value, then the conformal transducer induces an upper probability via this formulation. That is the maximum value that the conformal transducer attains on a specific measurable set for all possible measurable sets. Now, for those of you who are very acquainted with imprecise probabilities, you've seen that you can see that this is a consonant plausibility function, but for the purposes of the talk, I only care about it being an upper probability. And in turn, through this upper probability, I can derive a credal set. That is, this is what the economists call the core of the upper probability. That is, all the probabilities that are setwise dominated by this upper probability, upper bar pi. Yes. So what then I did is that we can formalize this procedure of extracting a credal set from the conformal procedure as a correspondence. In particular, give me the data that I've collected so far and the choice of nonconformity score. I will return a set of probabilities that you can see here. Again, I just opened it up so as to make it clear the dependency on the choice of the nonconformity score. And this credal set, this set of probabilities is a credal set under the consonance assumption. Also, interestingly enough, Ryan very recently also characterized the elements of this set. So we know that this set is non-empty, and we also know how the elements of this set look like. To say it as my PhD advisor used to say, this is not just a fart in the space to say, oh, we want to do some nice theory. This is something that we can actually characterize. We know how these elements look like. Okay. And finally, once we have derived this credal set, we can obtain from this credal set a confidence interval, a sort of a confidence interval, which we've shown in the past that it corresponds to the conformal prediction region. But let me be slow about this so that everything is clear. Okay, this point is because I presented this work to category theorists before. I know you all know what a conjugate lower probability is. Given so my credal set, what I want to extract from it is what is called the alpha level imprecise highest density region. That is, it's the smallest possible set to which the lower probability assigns a value, right? A lower probability of 1 minus alpha. And formally, this means that it is the intersection of all measurable sets to which the lower probability assigns value of at least 1 minus alpha. And this too, by the way, can be formalized as a correspondence. Okay, so what I'm telling you now is that we have a way of correspondize, right? Transforms it into a correspondence, the conformal prediction procedure. We can derive a credal set from the conformal transducer and make it as a correspondence, and likewise for extracting the imprecise highest density region. Now, this indirect way of obtaining a prediction region is very much linked to conformal prediction, because what my co-authors and I have shown in a NICEIPTA paper is that the alpha level imprecise highest density region associated with the credal set that derives from the conformal transducer is exactly equal to the conformal prediction region. So it also enjoys the same probabilistic guarantee. So in turn, this indirect way of obtaining a prediction region, first extracting the credal set and then deriving the prediction region, is equivalent to directly using conformal prediction. Now, although we showed this equality, this equality doesn't imply that the two procedures are equivalent, intrinsically equivalent. It's only telling us that the result of these two procedures is the same. But this indirect route to obtaining a prediction region is promising, right? It goes in the right direction to give us cardinal UQ capabilities of conformal prediction, and in particular, the cardinal UQ means uncertainty quantification. Capabilities are embedded in the credal set here, right? And so to actually fully answer my research question, I had to take a category-theoretic approach to the question. So, very briefly, category theory can be thought of a general theory of mathematical objects and their relationship. The main objects of interest are the so-called categories, unimaginatively, that are structure composed of two things, objects and morphisms. Objects are anything, could be sets, could be functions, could be banana peels, anything. And morphisms are relationship between them. So for example, if we have the set of the category of sets, one morphism could be the inclusion, for example, or something like that. And okay, so what I've first introduced is this structure that I called UH-cont. That is a structure that has for objects topological spaces and for morphisms upper hemicontinuous correspondences. Now, I suppose you can figure out why I was so fixated with correspondences before. Upper hemicontinuity here, it's a generalization of the notion of upper semicontinuity to the correspondence case. So I first showed that this is a well-defined category. That is, it satisfies desirable properties, among which the more important ones are composition, and it's closed with respect to composition and associativity. And what the main result on this part is that under minimal assumptions that I will discuss in the next slide, the conformal prediction correspondence that I introduced to you before, first is a morphism of this structure, sorry, is a morphism of this category. And then it's part of a commutative diagram, which involves first deriving the credal set and then extracting its imprecise size density region. And this in turn will allow us to tell that the two procedures are intrinsically equivalent. But let me not run too fast. Okay, so what are these conditions? They are four. The first one, and it's also the strongest one, is that the measurable space is compact and endowed with the Borel sigma field. Okay, so here there is a notation abuse. Here I should have written psi in F0 proper strict subset of calligraphic F. Basically, this F0 should be the functions that are invariant to permutation in their first argument, and also jointly continuous on yn and y. I didn't do that. I didn't do so to not, exceed with the notation. We also need the no-type parameter. That is the credibility level that we select must not be in this grid. This is not too much of a daunting requirement, because if it is, say that 0, 1 is in this grid, we can simply select alpha being 0.999 or 101, something like that. So we can easily avoid being in this grid of values. And finally, okay, this is more on the topological side, so it's fine. We need the space of probabilities to be endowed with the weak star topology, and the hyperspace of non-empty, convex, and weak star closed subsets of delta y to be endowed with the Vietoris topology. And what we have shown is that if 1 through 4 hold, so if these four assumptions hold, and the conformal transducer is consonant, we have that the full conformal prediction diagram commutes in the category that I introduced before, and the conditions are actually minimal. What does this mean, right? This seems very abstract and not very enlightening. But let me introduce a little pictorial representation so that it's easier. So this is what the full conformal prediction diagram looks like. It's telling us that given our data and given our the choice of the nonconformity score, once we fixate on one alpha, right? We block one alpha that satisfy not being in the grid Sn plus 1. It's equivalent to derive directly the conformal prediction region, or first deriving the credal set and using that credal set to have the imprecise size density region, which we know corresponds to the conformal prediction region. So this is what I was briefly mentioning before. The result that we had before, that is that the conformal prediction and imprecise size density regions are equivalent to each other, are not enough to tell us that the two methods are intrinsically equivalent to one another. They just told us that the product was the same, right? The outcome was the same. Instead, okay, a result like this tells us that we are on the right direction, right? At least when we look at the conformal prediction procedure as an upper hemicontinuous correspondence, this intrinsic equivalence is discovered. And this is kind of nice because since the credal set is indeed a credal set, we have a ton of existing metrics to endow it with a cardinal scale of uncertainty. Here we have just a few references, but in the paper there are more than 200. So please look at that. And not only that, but we are also able to quantify different types of uncertainties. This is something that machine learners like a lot. Different types of uncertainty being the reducible one that is called epistemic by machine learners, and the reducible one that is called aleatoric by ML people. And again, here you have a handful of references on the topic, but there are many more. Now, the uncertainty will be quote unquote marginal. That is, it's averaged over the possible realization of y, and this mimics the marginal guarantee of conformal prediction. And what we conjecture, and honestly, it's an open question as to how to prove this, is that the analyst controlled choices, that is the confidence level alpha and the non-conformity score psi, are primarily associated with epistemic uncertainty, whereas aleatoric uncertainty, I think, stems more from the intrinsic variability of the exchangeable process that we studied, that is the distribution P. Okay, so let me take a sip of water before I go on. Now, just again, in the spirit of my PhD advisor to show you that this is not just farting the space, I want to show you an ML-inspired example where these assumptions are actually met and they actually make sense. So if we let y be 0,1 to the power d, which is typically the case for pictures, with its Euclidean topology, we can let phi theta be a feed-forward neural network whose activation functions are continuous, for example, ReLU, which is continuous in both parameters and input. And then, given a training set and a candidate point y tilde, we define the nonconformity score as you see on the slide. This is, for those of you who are interested in machine learning or who work in machine learning, something that is well known and common. And I have in the next slide where 3 examples where something like this pops up in the literature. And it's easy to see that it's both permutation invariant and it satisfies the joint continuity assumption. Now, bear in mind that in this case, consonance is not guaranteed to hold, but we can enforce it, right? So what we can do, for example, is to consider the normalized conformal transducer, as you can see here. And this is something that Leonardo and Ryan studied extensively in the past, and they guarantee us that these are well-defined conformal transducers. So this example is interesting because it has a lot of implications in machine learning or where people use that kind of nonconformity score. For example, few-shot prototype learning, where the nonconformity score is the squared Euclidean distance to the class prototype mean. So again, very used in classification. Out of distribution detection, where we have a sort of a learn Malanobis style OOD score that looks like the nonconformity score that I had before. And finally, heteroskedastic conformal regression, where if phi theta, that is, remember, it's the ReLU network, it's basically this guy right here, right? It's a feed-forward ReLU network. Is the penultimate layer of a regression network, then psi is locally adaptive and valid prediction set, yields locally adaptive prediction sets. Okay, so this is, once again, for those of you who are into machine learning, you will have seen something like this somewhere or the other in the literature. And for those of you who are not in machine learning, this is simply to tell you that the conditions that I have given are not irrealistic. There are very, very well-studied cases in which they hold. Also, and this is perhaps even more surprising, the same full conformal prediction diagram commutes in a different category. So in this category, we have for objects, we needed here a little more structure because I wanted to be sure that the functional analytic ideas of continuity and measurability were both studied when I gave these results. Now, weak measurability, which is a weak notion of measurability for correspondences, is a nightmare to work with. So I needed a little extra mathematical structure to work with. In particular, I need this time objects to be compact Polish spaces with the Borel sigma algebra, and the morphisms, they need not only to be weakly measurable, but also uniformly compact valued correspondences. And what I've shown is that under essentially the same conditions as before plus consonants, the full conformal prediction diagram commutes here as well. So basically, the fact that this full conformal prediction diagram commutes in both of these categories, where we consider again continuity and measurability, then this is an assurance regarding the fact that conformal prediction actually does have cardinal uncertainty quantification capabilities via the credal set. Okay, so this is the first big result that I had in the paper. But then something else came up. So I was talking to my student, and she told me, oh, there is also a Bayesian version of conformal prediction where the nonconformity score, people have chosen as nonconformity score the negative posterior predictive distribution. And then I said to myself, oh, maybe there is a way of making conformal prediction to link everything together, right? Like a frequentist procedure like conformal prediction itself, a Bayesian one, and an imprecise one. So what I did is to define first a function that takes as input the data and a prior that admits a density. I mean, this is classical. And it spits out the data, so I don't forget the data, I carry them over. And also a nonconformity score that is, jointly continuous as before. In particular, this is the negative posterior predictive. The fact that this is a well-defined nonconformity score comes from a very nice paper by Fong and Holtz at Oxford. And I call this function BCP as an acronym for Bayesian conformal prediction. Also, I introduced a correspondence that basically gives me the alpha level set of the posterior predictive distribution. And in particular, it's telling me, give me an alpha, give me the data that you have, and give me a prior, and I will spit out the alpha level set of the posterior predictive. Okay, so the highest density region in a sense. And what I found is that under the same assumption as before, plus a few more, and in particular, so 1 through 4 plus consonants, and also the usual minimal technical machinery to ensure that Bayes works, and in particular that the posterior predictive is well-defined and depend continuously on both the data and the prior. What I found is this monster of a result, right? This monster of a theorem. And what this is telling you is the following. Once again, let me skip the math and go to the pictorial representation. It's telling you that this diagram commutes asymptotically. Now notice that the top right parts, the top right part of the diagram is the same as we had before for the full conformal prediction diagram. What's been added is this one here. So it's telling you the following. Suppose we have our data and we specify our prior. Now we use the data and the prior to derive the posterior predictive, and we extract the alpha level posterior predictive from it. And this gives us this direction here. Equivalently, we first derive the posterior predictive, select the negative posterior predictive as nonconformity score, and then derive the conformal prediction region. Or also equivalently, once I have the nonconformity score as the negative posterior predictive, I extract the credal set associated to the conformal transducer, and then extract the imprecise highest density region of that alpha level. Then asymptotically, all three procedures are equivalent to each other. And this is kind of interesting because it confirms an intuition that Ryan had in 2022 and that we kind of expanded on in our ICIPTA paper of a few months ago. That is that CP can be seen as a bridge, or at least keeps together, Bayesian frequentist and imprecise approaches to predictive statistical reasoning. In particular, oh, by the way, this I only showed in the category UH-cont because the other one was too much of a mess to work with. So in particular, when seen as upper hemicontinuous correspondences, the model-based Bayesian and imprecise methods and the model-free conformal construction yield asymptotically the same alpha-level prediction region. And I think this is pretty cool because it reveals a profound connection between these types of prediction mechanism that only apparently are very far from each other. Now, I think I've abused your patience, so let me go over the other results that I have in the paper, but that I chose not to present in depth here. The first one, and I think this is of great interest to the imprecise probabilistic community, is that under a minimal condition, an upper bound to the generalized base upper posterior is actually equal to an E posterior in the sense of Grunwald. And this hints at an arrow going in this direction from the bottom left to the top right. But I haven't been able to show it yet. Anyways, this is kind of an interesting result. And if you somehow are interested in E values, E posteriors, or somehow work with either Peter or Rianne, please reach out so we can talk about it later more deeply. Also, and this has a nice implication for AI privacy. You can frame the imprecise highest density region extraction, and therefore also the conformal prediction region derivation, as a functor between two categories. A functor, you can think of it as a function between two categories. And this buys you AI privacy implication, especially in federated learning, because basically you only have to share the local credal set instead of the whole data set that you work with. And finally, okay, because this paper also had this category-theoretic flavor to it, I studied some properties, that is the monad, the functors associated with the two categories that I mainly worked with. Good. So before I give you the conclusion, let me sip on water a little bit. So again, what we did is we took this category theory route to full conformal prediction to show its cardinal UQ capabilities. And as a byproduct of this result, we were able to prove that the conformal prediction methodology kind of bridges, or at least sits in between, a Bayesian frequentist and imprecise approach to statistical prediction. Now, of course, this being the first work of this kind, we barely touched the surface of what's to be known. For example, can we reverse engineer what we've done so far? That is, can we, by studying the categories that I've introduced, learn something about conformal prediction, some new properties that we don't know about? What's more, because the morphisms for these categories are correspondences, can we look at what are called Kleisli categories arising from the subcategories that admit a monad to study some properties about conformal prediction? This is kind of a continuation of the previous point, but it's basically telling you that there are some well-studied types of categories whose morphisms are set valid functions. And maybe by studying the subcategories of ours under that light, we will be able to find something new about conformal prediction. And finally, it would be nice to see whether conformal prediction could be framed or could be formed as a morphism of different categories, because it would be nice to get rid of the assumption that of the requirement that the space Y is compact. Even though it's not okay, a deal breaker, but still it would be nice to relax. Okay, so this is what I had to present to you today. Thank you very much for attending. And before I conclude, let me plug our recent workshop. So together with Creek and other co-authors, we were fortunate that our workshop on epistemic intelligence in machine learning was accepted to EURIPS 2025. You can see what the topics are about. basically anything that has to do with imprecise probabilities intersected with machine learning is more than welcome for submission. The submissions are non-archival, which means that they will not be published, but you will get a lot of very nice feedbacks for your work that you can then submit to other conferences or journals. It's going to be held in Copenhagen in the December 2 to 7 interval. I think our one is exactly on December 6th. Crick, tell me if I'm wrong. But yeah, looking forward to seeing you there. So thank you very much.